Hi guys, welcome back. Happy New Year. So we were in the middle of circular motion, and so the next topic we're going to talk about are circular orbits. I'll kind of comment a little bit on stuff that we talked about before, so we can refresh. But basically, to start talking about circular orbits, we are going to start with the flat Earth approximation. So we're talking about very small distances. We can approximate the Earth to be flat, although it's not, it's curved. Anyway, suppose we had a cannon and we could launch a projectile. So the range of this thing, which you should remember from, that's bad, but it depends on this initial velocity that we launch it with. So if I launch it, it'll shoot out and land on the ground. If I launch it at a faster speed, then it's going to go a little bit further and even further, right? We would get this kind of motion. But what happens if I take this incredibly large? Well, then we move away from the flat Earth approximation, and then we actually have to consider the curvature of the Earth. So the Earth, starts curving away. So if I can launch this fast enough, what you'll see is that it starts to curve sort of with the Earth. And so I'm gonna redraw. So if we imagine a terrible circle, how about I just do the circle tool? So, if we have, again, we're launching a projectile. We launch it with some velocity and then it'll hit. But if I launch it fast enough, as it starts falling, the Earth will curve away from it. And so it'll go all the way around. It's still falling, it's just that the Earth is moving. Because this thing is going so fast, it never collides. I'm drawing this terribly. Oh well, you're used to my bad drawings by now. And then it'll come back to where it was. And when this happens, then we call that an orbit. And so it's weird to think about because an orbit, a circular orbit, is just free fall. It's just falling around the Earth in a circle. So, and in free fall, we know that the acceleration or the force is the force of gravity. So the acceleration is g, because it's the force of gravity. The force of gravity is the only thing pulling this thing down. So when we do projectile, we say that it's straight down. But in fact, what it is it's towards the center of the Earth is the force of gravity. And we'll come back and we'll talk about Newton's theory of gravity. So we have this force that's always pointed towards the center. And any force pointed towards the center is called centripetal. So you can see how this all ties in. Okay. So let's think, what's happening? Well, we have an object that's in motion, in circular motion. We're going to say that it's very close to the surface of the Earth, so not very much. So our radius is going to be this right here. We'll just use the radius of the Earth. So the net force in this case is going to be the centripetal force times the centripetal acceleration. This is for an orbit, a circular orbit. Ellipticals get a little weird. So the net force acting on it is just that force of gravity. So we get the force of gravity is equal to the mass times, and then centripetal acceleration is just v squared over r, where r in this case is going to be the radius of the Earth. The force of gravity we've learned is m times g. So we get mass times v squared over re. Mass is gone. I can multiply this over and I'll take the square root. So the orbital velocity is equal to the square root of g times r. I'm going to just say r. It's whatever r is. In this case, it's re. So that's our orbital velocity. Now this is simplified. We're going to come back and redo this when we get the theory of gravity. but we can now use it. So let's think about our hypothetical cannon up here. We'll say it's like a meter above the Earth's surface. And we're going to launch it fast enough that projectile is going to go into orbit. Or you could think of like a baseball player. A baseball player hits a baseball. How fast do they have to hit it so that it goes into orbit? If there's no trees or mountains or anything, it's just an empty Earth. So let's figure that out. So the radius of the Earth is 6.37, 6.4. Oops. So 6.4 times 10 to the 6th meters. And so we can just do this. So the velocity to put it into orbit would be the root of g times the radius of Earth. And we get 7,919 meters per second, which is about 17,000 miles per hour, which is about 23 times the speed of sound. Which we refer to as Mach. So that'd be Mach 23. Fighter jets, I think, are about Mach 3, Mach 2, Mach 3. So that would be crazy fast. All right. But what if it's not at the surface? So what if we put it up in orbit, like the ISS? So what if the ISS is up here? How fast is that thing moving? So the ISS is in what we call low Earth orbit. Which is around 230 miles or so. Which is 230 miles above the surface. And that's 3.8 times 10 to the 5th meters. Okay, so low Earth orbit. So we have the ISS. If we want to know how fast it's going, then we can use the radius, but we're gonna have to add in the radius of the Earth. So it'd be the radius of the Earth plus the radius of the orbit. So this R orbit, this quantity here. So the velocity of the ISS would be root of g times radius of Earth plus 3.8 times 10 to the 5th. And we're using the radius of the Earth from above. So 6.4 times 10 to the 6th. Let's calculate that. So we get the velocity of the ISS to be about 8151 meters per second, which is faster than it is on Earth. And so this actually doesn't jive. This number is too big. Now the distance, that's fine, but it's going to be this g, and that's going to change. And we should know that as we get further and further away from an object, the acceleration due to gravity decreases. But we'll come back to that when we do the theory of gravity. But for now, that's our approximation. And since we know the velocity of the ISS, we can then determine how the period it is to go around, because that's just 2 pi r divided by the velocity. Remember, that's the r of the satellite, of where it is. And if you plug in the numbers there, you get a period of about 87 minutes, which is off. It's about 92, 93. So we're off by about 5 minutes. But that comes from this, which then comes from this. So we'll need to come back, and we'll do that in a couple weeks. We'll come back and we'll talk about gravity, and we'll fix this whole orbital thing. But for now, that's about all that you need to know. So just using circular motion, tying it to the force of gravity, and everything is good.